Okay, so let's get started. We built this system. I'm sure you've all, if you've seen the talk, you recognize it. So we have a mobile app and an app on a wearable device. We have Apple Watch now and a Pebble. And we might connect to a heart rate monitor or any other fitness device that you might have. We collect data as users exercise. We send the data for further analysis into our Akka cluster. This is where we keep all the state for all the users. We might run further analytics. We might actually learn new things. That's where the Spark code comes in. So we have gathered data from all the users. They've told us what exercise they've done, or we do the hard work if you don't want to participate. And then that means we have now improved our model. We can recognize more things, or we can be more successful in recognizing some of the things we recognized previously. So we push the model back to the mobile devices. We run the classification. All right, so we had this, we built this, and it was great, right? And then we actually took it to production, so to speak. We have a local gym, and we gave it to users, and yeah, it was terrible. None of it worked. So much so the users exercised, and because we did all the analytics in our Akka cluster, the delay, which was about a second and a half, that made it unusable. So that was the first problem. When the users finished their exercise, they went, oh, what did I do? 2, 3. And they hated the app. Second problem was that sometimes we even lost 3G connectivity or any kind of connectivity. So the users exercised and we did nothing. What made it even worse is because of these delays, we had no feedback on our machine learning models. Imagine that you go to the gym and exercise for an hour, and then you come back and push the result to your mobile and say, you've done all of this stuff, but could you tell me what you did 10 minutes in? Oh, I don't know. Could have been something, maybe nothing. So there was no way to improve, or it was actually very difficult to improve our models. We were sending all sorts of unnecessary data over the network. Now, again, from our testing, we found out that most users actually spend most of their time in the gym not exercising. That's quite bizarre, right? But most people actually sit down. So even though they were sitting down, we were sending all these accelerometer and heart rate traces over the network, which was completely pointless. We, of course, kept all our Amazon infrastructure busy computing these pointless things. So that was costing us money. So that wasn't great. So in other words, it was terrible. So what now? Well, we thought we need to improve the sensor and signal processing from the devices. We need much shorter experiment cycles. So the idea that someone goes and exercises, labels the data, we push it to our storage, and we can improve our models, retrain them, and see if we can reclassify everything. That needed to be much shorter. The code we had before, this would have been a day's exercise. With the improvements, this is now down to minutes. And most of the time is spent up doing the exercise, which is kind of what we wanted. And finally, no experts. So, of course, we looked at all these accelerometer traces, and we looked at the graphs, and we eyeballed them, and we said, I know, these are the features that identify exercise. Surely we're getting it right. And so we, humans, extracted about 15, 20 features from each exercise, and we were getting it so wrong, it was hard to believe. So, no experts. Let's just build something a bit better where I can just throw the raw data at the inputs and out comes, this was exercise B, C, or D, maybe even A. All right, so we've divided, this is the traditional Lambda architecture. The speed layer and the batch layer. Speed layer should get results immediately. Batch layers, we store up the same requests, and we do some further processing on them. So applied to our app, this was what we had. This was the failing model. So if anyone's trying to build a fitness analysis app, don't do that. That's just not going to work. We need to shift things around. So it's not going to be a massive change. We're just going to extend the speed layer, the thing that does the immediate analysis, and we're going to include the mobile phones in it. So we'll get the users to do a lot of the computation for us. And we'll actually do most of it on the phone. So imagine that we have trained the model somehow, we'll get to how, and we pushed it to the mobile phone. Now, the phone receives data from these very unreliable devices, but it can do the immediate classification. And so that the only thing that goes to the server is confirmation from the users, ideally. So in the best case scenario, the users will look at their phone and go, oh, yeah, this is it. Or maybe even enrich the information. So we've computed that the user has done exercise A, and the user might say, oh, actually, I've done 10 kilos of exercise A. That's great. Or the user might say, this was actually really hard. So we now have a confirmation that this particular trace of data from the sensors was exercise A, but we have a little bit more information for that particular user. So we then, back in the Spark world, we can then cluster these users and say, actually, we have, let's call them complete beginners, never ever exercised. They behave in a certain way. They need different models. And then we have whatever groups of users you might want to have. In the app that we have at the minute, we actually compute model per user because we have so few users. We can actually afford to run the computation. Hopefully, when we become a $1 billion startup, I'll take 10 million. It doesn't matter, right? But we'll need to cluster the users and say, well, actually, let's run the same number of training runs, but we'll have to bunch the users together. In any case, we are doing now more on the phone. So we are resilient and responsive. So here's an example of an accelerometer trace that we recorded from the watch. This is, I don't even know what exercise it was, but it gives you an idea of the happy scenario. Nearly happy, right? You can probably spot that there's something odd going on here. Users don't move that way. This is, 20G acceleration. That's not going to happen. So that's kind of odd, but okay. This isn't too bad. This is worse. So this was in the Pebble world, and it sometimes just forgets. There's no way to recover. We had all sorts of retry, buffering. We tried many, many, many different ways to solve the communication gaps, but the reality is that the hardware just doesn't do it. The original Pebble is 16-bit CPU. You get all of, I think, 16K of memory for your program and data, and it's not a real-time OS, so sometimes it just forgets. So we have to be able to deal with that. And then, of course, the final thing, let's get rid of human experts. That really didn't work for us. So let's move it back, and let's get rid of all of this horrible stuff, and let me show you what we've actually done. So we have sensor data. So first stab at the sensor data that we had, this was in C++, and we used OpenCV. And we used OpenCV for convenience because it had all of the signal processing functions baked in. So this is great. We can do smoothing. We can do frequency analysis in just one call. What we sort of missed out is the memory layout for these devices isn't completely great in OpenCV, or at least in the way that we've used it. So if you think about recording matrices, so like the samples, think about columns of X, Y, and Z, and the rows represent the number of each sample, 1, 2, 3, and so on. Add to it heart rate, add to it rotation. Well, then it becomes much easier, at least for the hardware, to encode it as a single array with a stride into the array. So in the first element, we have acceleration X. And in the second element of that array, we have Y and then Z. And in the fourth element, we have X again, as though it were on the second row. Now, that turns out to be really, really, really useful for doing all the analytic functions in using the DSPs and vector libraries that are available in the hardware. So we'll actually get to see this, but the difference between doing a naive loop, where you just iterate over all the elements and apply, I don't know, exponential to each of the element, versus using one of the BLAS or vectorlib functions is order of magnitude. So it takes 100 units of time to do that in a loop, and it takes 1 unit of time to use one of the vectorlib or BLAS functions to do something that we find useful. So that was the first change. to encode it in the sensor data structure. And then we have the actual classifier. So we use multi-layer perceptron, and the code that runs on the phone is just the forward propagation. So we give it the trained model with the structure of the network, the weights, the biases, and the activation functions. And when given a block of sensor data, we spit out a result of exercises that we've classified in the data. So this is quite nice, right? Writing this code feels really great. Unfortunately, it gets slightly worse because then it sort of needs to wire into the rest of the iOS code. And if anyone's been writing Objective-C, it's just it has these horrible names. So did end versus ended. I mean, it's just terrible. But of course, we didn't want to go against it. This is bad enough. This is worse. So who here has done Hibernate in the world of Java? Excellent. This is worse. This is core data. This is sort of like Hibernate, but much worse. This is like IBAT. It's terrible. In any case, the data has to persist because the devices might be out of range, and I get to travel, which isn't glamorous at all because I arrive somewhere and I go, so how much for a megabyte? You mean £3? No. So I need to store the data on the device that I can then send to the server that I can use to improve the model. So all of it has to be persisted. And it then gets even worse. You think Swift, this is nice, right? Modern language, immutable, functional. And then we do that sort of horror. We take a nice array and we construct an unsafe mutable pointer for it. And we just grab the memory and then we're going to do something with it. Nevertheless, those of you who have sort of played around with some neural networks and machine learning, you might recognize these functions. You might recognize sigmoid. You might recognize hyperbolic tan. You might recognize ReLU. This is done in one tick. This is all the support that you get either in the DSP, in the hardware, or in vectlib. So this stuff actually runs at pretty amazing speeds on the processors and on the devices versus actually typing it out in a loop. The price you pay for it is that horror of pointers. But it's worth doing. And if you get the structure of the input data right, you can just sort of stride into the array. So you can say for every element, in this case here we have stride 1, so every element, if I wanted to do just x's and I had 3 elements in the array, it would be stride 3, so every third. So that's all really quite useful. And then we have Xcode, and it's all just hideous. In any case, that's the mobile side of things. Some of the exercises, so this is what it looks like when you actually collect data. So these are the traces. Again, the stuff at the start where people set up, and then they do however many things that they've done. So even if, as a human, so this was our starting point, right? As humans, we looked at it, and never mind what these actually are. So that's actually easy to recognize, right? You can spot groups of exercises. And so say, okay, 1 and 2 look similar, and then 3, 4, 5, same kind of thing. So really our starting point was collecting all this data and then saying, surely a computer must be able to do that if we can do it as humans. And the rest of it was implementation detail. All right, next up, we have the Akka cluster, which receives all the data, persists the state. So we say we get data from the devices that are confirmed, classified, labeled data. It says the device has computed what it is, and the user has confirmed. Now, in our world, users confirm by not doing anything, because the idea is that you run the app and you get on with it. There's no fiddling, no buttons involved. I had to look at many, many other apps, and the whole process of exercising was go to the gym. Okay, so suppose I want to do, let's lift a bag, right? It's a complicated exercise. Okay, so what are you going to do? Okay, I'm going to lift a bag. So you have to look it up in the list. Okay, how many repetitions are you going to do? Oh, I don't know, 3. All right, how heavy is the bag? Okay, really? I just want to get on with it. So again, that's the main motivation. For training, so we have a use in physiotherapy where the users actually, under someone's guidance, train it. We have the luxury of per user model, so you can take the app and say, I'm going to do this. And the physiotherapist does whatever exercises the user has to do. The restriction, of course, being that the sensor has to be on the limb that moves. And then they save the data. And then we compute a new model that we can deliver to the phone. And so the next time the user exercises, again, we cannot yet give quality measurement. So to whoever is doing the exercise, we can't say, no, you're doing it well, or you're not doing it well, or you need to do 5 more. But we can actually measure progress. So the next time the physiotherapist sees the patient, can say, oh, okay, so you've done all this stuff, well done. Which is actually quite good, rather than selling this stuff to people who can afford to buy Apple Watch to go to the gym. Anyway, I get cynical. So all this data ends up in our Akka cluster, which we persist into some sort of journal, and then we read the journal for all the users, and we compute the new models in Spark. So let's see how it's done. Data arrives from the sensors, or rather from the mobile over the internet through ELB, and then we have, let's pick 2 services, just to illustrate the point. We have, I'll get it wrong, exercise service and profile service. I bet they're the other way around, but let's see what they do. And then, of course, we have push notifications. We could build in some sort of social media something. Let's not. All right. No, I was right. OK, so the orange one is user profile. So we receive user profile, typical stuff. Register, you say, oh, what's your username and password and whatever biometric data that we collect about you. Hits the user profile service, which in Akka and Spray's talk is the REST API, right? It's a thing that receives HTTP requests and somehow turns them into messages that we then send to the other components in the system. User profile processor in the CQRS world is the validator, right? So we check that, I don't know, username isn't yet taken. That's the easiest one. And then we have per user profile, right? So we then treat this distributed state, all the user profiles, as instances of a user profile actor. And these 3 lines, that's the little magic of cluster sharding. We have as many machines as we want to have, 3 in reality, but as many as you want to have. And each machine has some number of user profiles living on it. These are the views on the data that's kept in a journal and in snapshots. Excellent. No. User profile, exercise service, that's the thing, right? I mean, user registration, anyone can do it. It's practically the same story. The difference is we have a user exercise processor per active exercise session. So when the users tell us, I'm exercising, and if we have internet connection, we can give them more feedback. So the motivation, future versions will do some sort of motivational messages. More, harder, some along those lines. And then we have views on the same data. So this is analytics. So someone might do the exercise session and say, okay, so what have I done? Well, let's review all my exercise sessions. Let's review my exercise programs. Let's have a look at how much weight I've lost, gained, whatever your thing is. All right, so we'll whiz through the code. To me, this is readable. Hopefully to you who have, everyone's happy? Okay, stunned silence, that's good too. Usual business, APIs, right? Get and post, so I can check particular user, I can set an image, I can register an iOS device for push notifications, I can register an Android device for push notifications. That data, these HTTP requests got turned into messages that this processor actor receives, so this is the validator, right? So let's go through a registration flow. Someone clicks in, I want to register, all right, well, that's nice and easy. First, best case scenario, as far as our program is concerned, the username is already taken. We have nothing left to do. We check whether the account already contains the email address. If it does, reply back with a value on the left that says username already taken. That's some sort of 400 message that goes back to whoever's requesting it. Slightly worse for us is a scenario where the user register message arrives and we don't have the user account, so we have to do something about it. Persist the message, so it ends up in the journal, so if this guy crashes, we can replay back and never forget anything. We will create a new user profile in the cluster. We'll mutate our accounts, save a snapshots just so we don't have to do things over and over again, and reply to the API to whoever called us with, a value on the right that gets translated to 200 saying, yeah, this is your UUID. Excellent. And that all works really well if we only had just one node. But this user profile processor might be, on multiple nodes. And it is. In fact, there's one on every node. And that was good, except there is this thing, right? User accounts. This is our state, even here. So it has a fancy name, known accounts, but imagine a map. Well, now what? Now if I register on this node, that says, OK, you've registered, it ends up in a journal, all jolly good. Now the second registration message goes here, say with the same email address. So I won't be able to detect it. The middle case is actually a nice, happy scenario because I save a snapshot every time I register. When this new user profile processor that sits in the middle gets created, it gets recovered from the snapshot, so it sees the state that, whatever the last snapshot was in. So to make it work, we have to connect them with some sort of message bus that shares the state. And you might be thinking, oh, this is how it's done in code, and you might be thinking, well, but it could be inconsistent. Well, yeah, it could be. In this case, we favored availability over consistency. It has to be partition tolerant, right? Because we're on Amazon, and I don't like to pay money, so we're on the cheapest machines. So they will fail. And I'm thinking this is a billion-dollar startup idea. Again, I'll take your checks after the talk. So let's be available, right? Let's allow the users to register. Let's allow the system to stay alive, even if thousands and thousands and thousands of users are registering. It means that there is the odd user that will fail, right? So this guy. When a message is received from this pub/sub bus, from someone other than me, this is where I have a chance to detect that I've let someone else in. It's too late because I've actually let both of them in, but I can do something about it here. My thinking is this is a user interface problem. We'll just forget the other user. But your program might want to do something else. User profile, this is now the same story. It's a state. Now this is a lot easier. I have an actor that has a var state. So it's this mutable state. The state is encapsulated inside the actor. The actor is distributed across my cluster using cluster sharding. And all I have to do is send it messages. And then it's nice and easy because, consider this. If you went to the pendulum talk, one of the points was, let's not do all this busy work. By that I mean, if I have a user that is registered in my system, and I say, OK, give me my profile. Well, I don't want to go to the database to load the profile because, well, I actually have it here. It's in the state. The state lives somewhere in the cluster. And the cluster sharding code actually ensures that this will get removed from memory if it's not used very often. So you don't want to have all these users in memory. But this is a nice and easy way of doing it, right? No select star from something or MongoDB internet. Never mind. I'm calm. It's all good. It's all good. We just reply with what we have in memory. All right. Exercising, it's the same thing. Right? We receive a session, persist it, and then we can do something about it. So that's the upper cluster. Now we have Spark. Now what, right? So we have all this data, all this labeled data, and we need to process it. I said that at the minute, we run the training program per user. So if all of you download the app, and if you have the secret URL that you can send the data to, we will train the model for you, for your exercises. So if you decide to do something completely crazy, we can recognize it for you specifically. So that thing, how do we do it? Well, first thing that we need to solve, and if you're writing these kinds of systems, first thing you have to solve is the journal. Now, it was all really great in the Scala world when I could say persist. So have some message, persist it in the journal, and then read it back. Great. Does anyone know how it works by default? Persist, what happens then? So the horrible secret is that the message gets turned into bytes. OK, so far so good, using Java serialization. And that's terrible, right? So then all I have to do is add one more field, and that's it, boom. Or even use different version of Scala, which is usually a problem anyhow. But on top of everything, right, now you can't read your messages from the journal. So that's a bit of a problem, and it's slow. Did I mention that? It's terribly slow. So that monster in the journal, right? If you just keep persisting things into the journal and then want to read them, it will fail completely. So we want something better, something that's fast, stable. Compatible is a bit of an odd word, right? But if you have, let's say you have your shiny new Akka cluster that uses Scala to whatever it is, 12 or Dotty or something. But then you have to analyze it, you have to run it in Spark. And Spark is slightly more conservative in its uses of Scala. So you might actually be a big point version of Scala off. And even if somehow you manage to get everything built on the same version of Scala, this is a bit of an architectural smell, right? You don't want to be in this fragile position. So you need to have code that can read both things. You also need to have code that plays well with all the libraries that are baked into Spark. So if you're thinking, I know, I'll use Creo. I know I'll use Protobuf. I know I'll use this. You have to be very careful and select, by a process of horrible trial and error, version that plays well on both sides. What does work at the minute is Creo and Chill. So Creo and Chill is a library that defines a particular format that is compatible both on the Spark side and the Scala side. And all that you have to do in your configuration is say, these are the types that Akka should use to persist messages in that particular format. And then you can read both ends on the Spark side as well as the Scala side. So that's actually quite useful, which was a really painful exercise. Well, now what? Now we have all the events in the journal. So now we can read everything that we persist, which is kind of nice. We add to it the Spark Analytics code for Cassandra. And now we get to see event table, which is everything, all the events that got in by calling persist. Excellent. Well, except now, of course, it's every event. So we need to do something more about it. We need to write this program that we then submit to the Spark cluster in a way that filters out maybe some of the data, that maps them and transforms them in a useful way, maybe like this. So what we want to do, we want to read all the events. We can't escape from that. But we only want to pull out those that represent the entire session, right? So the user, when they stop exercising, they say, okay, I'm done. The mobile discovers that it's online. It submits all the labeled data. And we have it, right? So this is all the accelerometer traces with the right labels, with confirmation from the users. So we want to take all the events that we had and pick out only the ones for a particular user. We'll only pick out the correct examples. So these are the confirmations. Yes, the user has said that this is indeed exercise so-and-so. Group them by user ID. Remember, we were doing it per user. And then, okay, you might start with just dumping the files in a CSV file. So you clone the code and you run this, and out comes a collection of CSV files that have essentially accelerometer traces and labels. Oh, now what? Well, this is what they look like, right? So I took a few. So you might run a program and, again, completely unfiltered data. This is what actually arrives from the sensors. And then you train it. And we'll get to a training program. So this was in the days before the Spark MLP implementation. Now there is actually a multi-layer perceptron implementation in Spark that you can parallelize. So unfortunately, we don't do that yet. We do really stupid parallelization. And the MLP, the backpropagation, is done in one thread, if you like. And we parallelize very naively per user. We have 100, so that kind of adds up really well. Now, on these exercises that I've selected, we're doing actually really pretty well. Now, they're big exercises and tuned for this talk, but even with larger exercise sets, the success rate is actually really good. Okay, here's another one. Except this isn't any old exercise. The big problem that we have is exercise versus no exercise. So users are walking around, right? And I can pick up something and do exercise, and then I stop. Now, if the users just stopped and did that and not moved at all, that would be kind of nice. But they don't. They keep walking around and they fiddle with their phones. So we need to find a way to detect exercise from no exercise. Now, it wouldn't make sense to build classifiers. So one idea is to say, okay, well, we have all these classes, exercise A, exercise B, exercise C. We can train the multi-layer perceptron to recognize A, B, and C. And we could add one more label, D, that says, and everything else. But it's actually quite useful to balance the number of inputs for each class. So you'd have to have, I don't know, you'd have 100 inputs for class A, 100 examples for class B, 100 examples for class C. And now everything else, presumably everything else is quite a lot of things. So that doesn't really work. What we have at the minute is two classifiers. One that does exercise versus, as we call it here, slacking, which is reasonably successful, right? And exercises all the exercises. So we only have two classes, and given our training data, it's not too bad. And then only for the blocks where we do exercise, we actually attempt to say, well, here's what it was. All right. You know what? We have a demo. How about that? Don't worry, I won't exercise. So, okay. So we have this Swift playground. This is the first thing we want to do. So I have, let's run it, right? So I have collected some data. And just to see, so here's one. So this is x-axis, the stride is 0, the first element. So if I change it to 1, we'll go element 1, and then +3, which is 4, and then +3, which is 7, and then I'm lost. But you get the idea. And this is 1,000 samples, and we sample at 50 hertz, or rather the hardware here samples at 50 hertz. So, this is what? I don't know, many, many seconds. This isn't my good day. Anyway, here's what it looks like. So how about this classifier, right? So it should be really easy to just uncomment that. Now, I've built one for the demo. It's called demo. So what's happening here, right? So let's have a look. It has this named thing, and then it has layer config and labels. So labels, that's probably pretty clear. These are the three classes it can recognize, whatever they may be, right? Layer config, well, that sort of looks like the number of perceptrons in each layer. So we have 1,200 at the input, which means that we throw at it 1,200 values. So 400 in X, Y, and Z. Because we sample at 50 hertz, it is 8 seconds worth of data. So we looked at all the exercises that users do, and even big exercises like squats, they take less than 8 seconds. Or to put it another way, if you're taking more than 8 seconds, you're not doing it hard enough, and we won't recognize it. But we have 1,200 at the input, and we have 3 layers, 3 neurons at the output, so 3 labels. Out will come 3 numbers. And the last thing we want, the difficult stuff, is the weights. So if you look at how we load it, we grab the weights of type raw, but just an array of floats dumped into a file. And those represent the weights between the neurons in the layer. So presumably we could just run this now again. Load the same thing. Well, that's not. See, yeah, that's not good. I mean, luckily I practiced, so this is okay. What's happening is that we're missing this file demo, right? So we're trying to load this. No. Come on, we're trying to load demo from the resources which represent the weights, and we don't have one. So how do we get our hands on this model? Well, we train it, right? Nice and easy. So we have a whole bunch of Python code that I can run that has the labels. Let me show you the data first. So let's try that, right? This is the model that we're going to train, and it has exercise. And as I said, this is nothing too complicated, right? It has the accelerometer traces and the label. Nothing else to it. There's a whole bunch of labeled files. So that's all there is to it. So we just run this Python program. We give it the data, so where it should get the labeled sources. We have some visualization. We can see it's going to all look wonderful. Let's just run it. OK, so here are the examples. Yeah, now it fails again. So the problem in this particular case is what I have deleted is the way in which we construct the network. So if you notice, again, I'll get into details of it. The network that we've constructed, and it has to match the iOS side. We have 1,200 inputs, and then we have a layer that has 250 neurons. It's the one below. And then we have 100, and then we have a 3. So looking at our Python code, this is nearly right? 250, middle layer, defining an activation function. So this is just a threshold. And then we have another function, 100 neurons lower, just a threshold again. And what we're missing here is the final one, just to construct the entire network. Now, I'll paste that in. You wouldn't normally type it in code, right? So if you're actually running this at scale, you need another program that discovers what the best shape of this network is. What are the activation functions that it should use? We have a sigmoid here at the output. So now I can run my training program. It's going to load all the data. And there you go. It's going to do things. So we have 10 epochs with all the labeled data that I have running through network that has 1,200 inputs and 250, 100, and 3 at the output with these biases and activation functions. What that's going to give out is spit a couple of files that represent the labels, the shape of the network, and ultimately the weights. That's what we really want to do now. And there you go. So this is actually doing pretty well, right? So from all the exercises, it gets it wrong in 0.7% of the cases, which is not bad at all. So you can download this program, download the training data, and have a go. So you can actually see what it spat out. There's an output directory. So here's an example. So it just picks the same charts that you've seen in the talk. So this is one of the examples that it picked out. It also produces evaluation. So this is how we're doing with that data set. So this is like less massaged than the one you saw in the talk where these were zeros. I mean, that's just not going to happen, right? In this case, we get it right for biceps curl in 900 cases, get it wrong in 10. So this is doing reasonably well. And finally, we have the weights. So all I have to do, yes, this is all very nice. So all I have to do is drop in the weights file, like so. And presumably that will be it, right? So I can now run the playground again. I'm just going to load the weights in my classifier, and all will be good, right? There we go. Okay, that's going to look the same. All right. So it's done something. We have some output on the console. All right. Well, okay. It would be useful to have some output, right? So let's actually do the classification. Result is exercise classifier. Come on. It does code completion when it likes it. Classify. This is the sensor data block. Let's have 10 results at the most. Doesn't really matter because we have 3 labels anyhow. This throws an exception, so we can just make it shut up by saying try bang, which is essentially try and catch an on-catch fatal error. So that's kind of nice, right? This is proper code. We don't even log the exception. We'll just crash. Anyway, and then for the result, for each, let's print that thing, right? See, I mean, Swift it's annoyingly almost good. It's like tiny little bits are missing. It would be ever so useful not to have to construct a function literal here, but okay. So we've done the classification, but I mean, if you look at the results, these are the classification results for each window. As we've run this 400 pixels, 400 samples long window, it says, okay, well, that's good. But this thing here, that really shouldn't be happening, right? I was expecting a number between 0 and 1, not, I mean, 26 is kind of good, right? I mean, it's super, like, 3,000% sure that it's the right thing, but it gets, well, okay, 11 is not too bad. Right, so it seems that we have some sort of problem in the way that we run the evaluation. And the problem is that I've been trigger happy with delete at our activation functions. So remember what I said about vector libraries and vector code, particularly in iOS, right? We could have written just a for loop here, right? So for every element, let's do, oh, I don't know. I mean, real would be easy. Hyperbolic tan would be nice and easy. But it would be it is even better to use the vector functions. Now, if you look at their prototypes, they actually do look a bit scary. Right? Unsafe mutable pointer float to unsafe pointer float to unsafe pointer UN30. It just looks ugly. It's because it's a direct translation of the BLAS and sparse BLAS and vectorlib code that's been with us since the days of Fortran. So actual implementation then goes to a pointer to float and const pointer to float. So the only thing to make it work in Swift is that you have to do this pointer gymnastics, really, to get it to work. Well, now that I've successfully pasted that in, we can go back to our worksheet, and hopefully we'll get some reasonable results. So let's see. Again, the same thing we've seen before. Oh, now it looks better. Does it? Yes. So these are the actual results with a much better confidence. We don't predict repetitions just yet in that code. But of course, there is code in the playground that you can have a look at that does repetition estimation. Now, this is all really good, and we're nearly done, I promise. But the actual demo, of course, is the thing that moves. Now, again, don't worry, I'm not going to exercise because it's sort of difficult to see what I have on the watch. But, so this, when you run it, at least in the, bloody hell, that's a little ambitious, isn't it? All right. So when you run it on the watch, get a little view. You can see that. That connects. No, different simulator. Come on. Yep. And that. Oh, come on. There we go. Right. So this is the user interface that you would get on the watch. Now, if I were doing it for real, just press start and get on with it. It records the accelerometer data, keeps them in memory. Let's not do that now, mainly because the simulator doesn't have accelerometer support, which is really great, isn't it? Never mind. I can run the controlling application and start demo. And these are actual accelerometer traces that I've recorded. So when I press one of these buttons, it's as though I've done that particular exercise as accelerometer traces. Push that in, we run the classification immediately on the device. And this is, it's actually fairly miserable to see, isn't it? Just so you believe me, it actually done that. It has actually done that. The length of time and what it was. I can do another one. And there it is. Ta-da! I can now stop the session. And if I had everything wired up, this would then go to the server. This has now stopped. The session is over because I pressed stop on the watch. But now I have confirmed examples that are stored in the database on the device. When connected to the server, they end up in our Akka cluster, which end up in a journal, which end up in a Spark program, and I can spit out a new model with improved classification. So that's it. There are a couple of things that are missing. How to find the best shape of the perceptrons. Yeah, that's magic. How to train it at speed, right? So you have 1,000 users. That's magic. How to get the training data. That, in particular, is magic. How to build the infrastructure. Magic. Actually, not magic. Come and see it at Scala Exchange. We'll have all the infrastructure with GPUs. All right. Thanks very much.
Yeah, I think we're out of time, so we can take our questions offline. But thank you for the very cool interactive demo, and
my pleasure. All right.
to learn more about it.
Keep cloning. There's the code. Have a look.